My name's David Pryce. I'm from Wandera, which is a mobile cybersecurity startup. Yes, I'm British. No, I'm not a bad guy from the movies. But I will be talking about the bad guys out there who are trying to get mobile malware onto enterprise devices and how we detect that using Apache Spark. So here's the summary. Of course, I'll outline the overall problem, what sort of malware we see out there, how it gets onto the devices. Then I'll move into the real data science of the problem, the data, the features, the machine learning itself, and then, of course, why we would want to use Apache Spark at all. And finally, I'll look at how we actually do that in production, and, of course, as always, a little bit of a pitch for data science at Wandera. So, firstly, the power of enterprise mobility. So we've seen a lot of change in the last few years around how mobile phones and devices like iPads are used in enterprises. And that's because of many reasons. As you can see here, the sort of seamless communication internally with email, Slack, WhatsApp, etc. How it adds hours of work in flexibility, so people can email from home. I mean, all of us here probably on Slack, you can talk to people at every point in the day, as soon as you wake up, etc. The access to these tools and these apps is much easier through your MDM or through your Apple Store, your Google Play Store. And finally, that these services are available everywhere at any time in the world. But this leads to many other issues that we don't necessarily think of. So the obvious things are security threats, appropriate usage. We don't really want all of our users to be looking at porn all the time and things like that. And this then means that things like costs spiral out of control. So large enterprises will be racking up huge bills where their users are just going on everything they can all the time. And that, again, in itself exposes massive data risks. Let's just build this one out. So that basically builds a happy hunting ground for attackers. So here's some big stats around that. The number of high-severity threats grew by 435% in 2016. 80% of organizations experienced a phishing attack. Now, phishing is probably something you've heard of all the time, obviously, through email, etc., but that's actually one of the main avenues that people get malware onto devices. 38% of hackers bypass standard endpoint defense, so that's things like Kaspersky, the AV you have on your machines by using social engineering. And finally, in 2016, we saw a 100% increase in mobile malware. Gartner are quoted here saying that mobile threats can no longer be ignored. So what do we do to get around this? Well, I can introduce to you now the product that we offer, which is a secure mobile gateway, which offers both an on-device protection through an app that we use and a network protection. So we can see all the traffic that the users that are deployed on our system go through. So we see all their traffic, all the apps they download, all the apps they install, as well as the traffic that those apps create. And here again, just reiterating my point that the mobile malware increases year on year. This is data from 2017. I think it exceeded that forecast. But this is just for Android. We see the same in iOS, in Windows, and in various other platforms. But our objective isn't just to identify, we also want to classify. So here we see this great, I love this plot here. It's almost like the periodic table for malware. And we don't just want to be knowing exactly what we have in terms of malware or not. We want to be able to say, okay, this is ransomware, or this is spyware, this is banker, et cetera, et cetera. And this then means that we can differentiate ourselves from the competition because we can be able to say that effectively and quickly so that we can then remediate the threat in the right way. So why is this any different to any sort of a problem that we've seen in malware on your laptops that we already kind of could argue is solved? Well, as I've already mentioned, mobile malware is on the rise. And that means that standard signature-based detection is no longer scalable or effective. We need a solution that can work across both what we know already and stuff that is new and unknown to the system. So this can now effectively protect our customers, but also then enable us to do more research. So from having a new system that can detect new threats, we can then take that information back to our researchers and to our data science teams and build new models, new threat detection systems that can then potentially find the next new 0 day. So the first solution for this is signatures and lists. We see that in things like Sophos and other community-based lists. But our solution and many other companies have moved from that list-based into the machine learning paradigm. So now that's the problem. I'll move on to the data that we will try and gather to then build the correct model. So an obvious way to go in terms of detection is I want a list of good apps and bad apps. The sources for these, as I've already mentioned, I guess, are things like the Apple Store, Google Play Store, and even our own gateway where we can see users are downloading certain apps. We add this together with our third-party threat intelligence and our inbuilt threat intelligence to seek labels. So in data science terminology, this then becomes a supervised learning problem. What we have currently is around 2 million labeled apps. Whilst this isn't a huge amount, when you start thinking about the features that they then generate, this becomes a very large data set. And on those features, we have all sorts of features that we will try and extract from a single app, APK, depending on the OS we're looking at. The three main areas we look at are structural features, so things like the permissions you see, the pictures in the files, the size of the certain file, the number of classes that you see in the code, and also the second area is statistical features, so that's things like counts, averages, do you see a certain type of email or domain name in there? And then finally, empirical features, so that's, does it have an executable file which maybe is malicious or isn't malicious? Do they register some sort of special signature that you didn't see before? Now, the way that we would handle these features is different from a normal problem. We couldn't just say, yes, binary has or doesn't have a signature, or does have or doesn't have an activity. This is because, as we'll see in the next slide, over all apps globally, there are potentially 500,000, if not more, unique fields that you could have here. And a typical app will only have 10 plus. So, for example, I don't know, the Facebook app, it will want to be able to use the phone camera. It will also want to use certain other signatures that you won't see elsewhere. So we can never really have this massive sparse vector where we'll have basically lots of zeros and just one for the camera signature. You want to be able to say, to recall that feature quickly. And the way we get around that is with a hashing function. The reason we do this is it allows for quicker retrieval over this what initially is a sparse vector, and it then creates this dense vector that if it has a big enough hashing map, it avoids clashes. So we typically use a map that's 2 to the power 20, so it's a huge hashing map. We do that so that we don't have hash clashes. So now we have data, we have labels from our third parties, and now we want to train a machine learning model. We initially tried many models in Spark, logistic regression, SVM, decision tree. We finally stuck with logistic regression. The main reasons for this were that it was understandable to our shareholders, it was quicker to train than some of the other two, and it was very understandable. We could quickly disseminate from a given prediction to which features were important. Again, that's difficult with the hashing function, and therefore give a bit more understanding to the business. Now, again, luckily, this means we don't have very many parameters. Here in Spark, you only really have one parameter for logistic regression, but we still wish to do cross-validation, so we get the best model at every point. We did this with k-fold cross-validation, and in general, we get an accuracy of 0.96. Now, accuracy, as you probably had mentioned earlier in the PayPal talk, is not the best measure, since you have, if you have any skew in your data, you will have a misrepresentation. So we also optimize on other measures as well. And again, as the PayPal guy mentioned, F1 is a good measure of this, because if you have imbalance, that's a very good way of balancing between precision and recall. And in this problem, we do have a lot of imbalance, because as you would imagine, there isn't much malware out there, but there's a hell of a lot of good stuff as well. So I've kind of already mentioned why we would use Apache Spark, but as all of you here are advocates of it, it's obvious why we would use it, I guess, is that it's truly big data. Whilst there are millions of data points, there are also millions of fields. So it's not just the depth of the data, it's also the width of it. The ease of use. So not only can our data engineers implement it and use it, but also someone like me, a data scientist, can go quickly from doing exploration to having an app running in their local machine, to then having it running on a cluster, so that they then have a very much a scalable solution, which is obviously the next point. So it's very easy to go from my laptop up to a cluster in AWS. And thirdly, the model persistence is actually inbuilt. So we already use the PMML paradigm, which you can see in the SparkML class. This makes it a lot easier to go from the model to having it in a REST API, which is then usable within our microservice environment. So how do we do it? We store all the data predominantly in Mongo or S3, but we take that data, we run the feature extraction using the Spark core programming, and then using the MLib or ML, we train the model, run the feature selection, and export to, as I mentioned, the PMML. This is then saved to S3, and whenever that happens, it's picked up by our CI tool, in this case Jenkins, to then deploy within our infrastructure. Here we use a paradigm, again, called OpenScoring, which is basically our RESTful API, so that when a new user installs an app, it calls out to this service. So just to cover what PMML is, because I think I've probably breezed a bit over it, it stands for the Predictive Model Markup Language. It is an industry standard, but there are many others. I think I saw a talk yesterday that talked about the PFA, which is an upcoming standard that basically is a change. This is a markup language, so it looks a lot like XML, whereas PFA is JSON-based. The pros for using it is it's language agnostic, so we can create models in Python or Spark and then export them to PMML and therefore have the same functionality across those two. It works in, as I mentioned, a REST API microservice way, and it has very good algorithmic coverage. So as I mentioned, if you did it in Python, you would use something like scikit-learn. You could be creating a logistic regression or a random forest there, then export to PMML. You would do exactly the same in Scala. So you would create your gradient boosted tree, export that out to your PMML, and have exactly the same functionality that you would have in Python. The bad thing is that because it's XML and because it has to list all the features you use, all the sort of weights you're using, it can create some very large file sizes. I think for this particular model, it was in the megabytes, tens of megabytes sort of region, and when you're then trying to take that file and deploy it into production in a way that doesn't stop the service for too long, you get some big problems. So we had some workarounds for that. Which I'll talk about in just a second. But actually saving to PMML was a very great, a big learning curve. In the RDD MLib library, it's already, as I said, already there, but the functionality hasn't quite moved over to the data frame API yet. So we had to work our way around it and fork our own version of the exporter. We also had to sort of hack our way around how the export happens. So natively, it will just give you the classes. So you'll be like, okay, I want a prediction, and the output would be, yes, it's malware, or no, it's safe. But we wanted to be able to control the way in which we tagged up our applications. So we wanted to get probabilities rather than just the class. So we had to basically add that functionality back into the exploitation of the PMML. And as I just mentioned, the size of the model is on average around 20 megabytes. We had to find a way to cut this down. So to do this, we did things that very similar to how TensorFlow packages up their models for the mobile application. We had to cut things like doubles down so that they gave more memory back to the user, but still gave the right prediction in the right way. So you have to be very careful in how we did that, but it took a lot of iteration around that. But the overall training time for this model can be tuned, obviously, as we just add more nodes to our cluster. But in general, we have a training time of around 2 hours, which for us is very good. That means we can do that offline, check our model, run it through QA, and then promote that to production. So how does it actually happen live? So what happens is a user will install a new app. Our app will then tell us, oh, the user has installed a new app. Here are all the features that you require. It sends all those features that I spoke about, so signatures, activities, to our backend. The backend then transforms those into the requirements for the model, sends that to the REST API. That's scored by OpenScoring, and that is then sent back to the service. Once that comes back with some sort of score saying, okay, I've got this new app, it has a score 0.7 or whatever, we then do two things. So we only ever investigate anything with a score greater than 0.9 because we want to be super certain that we found some malware. We don't want to be telling our clients that they have malware and then discover later on, actually, no, this is just Facebook or Netflix app. That would be bad, although you do find some variants of Facebook that aren't great. So from there, we then firstly we investigate if potentially we don't want to be, as I say, we don't want to be sending the wrong message. But our threat ops team will go away. They'll look at the APK itself. It basically gives them a triage list of things they should look into, and then finally we'll notify. This has been able to detect 0 days in the last 6 months or so. Famously, if you want to Google it, you should Google Reddrop, which was our 0-day malware that we discovered, which was a variant of some sort of ransomware. I'm a bit ahead of time, so I'll do a quick plug. The data science team at Wandera is fairly new. We do take some very innovative research and scalable architecture to pull that all together into one team, based mostly in London. There are some guys out in the Czech Republic and here in San Francisco to basically tackle these sort of problems. So malware detection is just one problem that we've looked into, but we also have a very big proportion of time spent in anomaly detection, phishing detection, and various other behavioral and user behavior models that we use to basically to protect and make sure our devices are compliant with various regulations as well as cost and data savings. Thanks for listening. As I say, I'm fairly early in finishing, so I'm happy to take any questions, and thanks again.
Dennis, EPAM System, I have a question. So you mentioned that you choose logistic regression, and you also mentioned that the size of the image of the model is like more than 20 megabytes. I kind of confused because in my best knowledge, basically to persist logistic regression, you should only persist weights, right? So like any reason why it's so big?
Yeah, so the question is around when you persist the logistic regression, you would traditionally persist just the weights. Yes, but in the PMML standard, you also have to have a dictionary of all the fields that you're going to use because it's basically going to go from the point where you feed it data to then giving you a response. So it has to understand something around the actual fields it's going to see, as well as the weights that the actual machine learning weights that it's going to use. So it's kind of all-contained model. It doesn't just know, oh, okay, when I see this one thing, I give it a weight X, Y, Z. It also has to know exactly what those fields are and what type it's expecting. So it's basically a bit of fault tolerance as well.
I see. Well, the second question, and before I made this just remark, like, since you have to send some data on your web service to figure it out the score, isn't like it's not really secure because malware can block your request basically, and like kind of
I think
make it always scored in a low level.
I think I don't quite know what the question is, but I think you're saying will malware block the service?
Yeah.
We don't actually send the actual malware packet. We do the feature extraction on the device, and those features are sent through the web service.
Yeah, exactly.
So yes, you could the malware, if they knew that we were doing that,
yeah,
could
obviously.
do that. But the next step that we have is to use machine learning on the device itself. So to use something like TensorFlow with their Android APK or their iOS APK, SDK, sorry. And then implement a model within the device itself.
Yeah, that's why I was asking why model's so big, so you can.
Yeah, I think initially we just wanted to get something that would work, and we were already getting those features within our service, so it was easy.
I see. Sorry for guys waiting. And last question, since I'm a bit late here, and you mentioned that you have MongoDB as your main source of the data. Any kind of issue with scalability? When you keep all data and extract it for your training from MongoDB?
The question is around
the scalability of MongoDB as the main data source for your training.
Right, okay, I see. I don't think we have any problems with stability. So we've been able to store millions and millions of APKs already with the features extracted, so we don't have to do anything clever with it. We just pull straight through Spark, through the Mongo connector.
Oh, sorry. So you mentioned you use a hash function for converting the not dense vectors into dense vectors. Why don't you use embeddings?
I say again, embeddings. Right, yes, we did try embeddings, but I think it was to do with latency of the actual, the application of using the embeddings in our service. So it was much quicker to use a hashing function because the implementation was just speed. And latency is a big problem when we're using mobile phones, right? So we don't want to stall the install for too long, basically.
And then my other question was in your drawing, you had a drawing of like the 4 steps you have during training. So how does it split? How does the 2 hours on a cluster split among those 4? Do you know?
Oh, that's a good question, actually. I'm not 100% sure. I think most of the time is actually spent in training and cross-validation. That's a good question, though. I imagine it's like that, though, because when I've looked at logs recently, that's what I've seen most, is just creating the separate models for each parameter set.
Because grabbing the data, I imagine, from Mongo could be slow, especially if you're doing all this.
But you're right, but they're in the same VPC and they're in the same subnet, so it's really quick and easy that way.
Oh, okay. Thank you.
No worries.
Did you guys leverage Spark to do any feature extraction, like specifically like putting the binary up there and then doing strings across that, or was it all done on the endpoint?
So the question is, did we use Spark for feature extraction?
Yeah.
Yes, the feature extraction is all done in Spark, but if we can, we try and do it a bit offline because it's just a bit quicker.
Okay.
But in terms of the actual training, yes. In terms of the scoring, no, it's all done in Java. So.
Okay.
So many questions. It's great.
Yeah. On your second to last slide, you mentioned you use 0.9 as your threshold.
Yes.
And what's the logic behind the 0.9?
So we did a lot of testing to see, we would basically look at our confusion matrix and we would slide through our probabilities.
Right.
And it got to a point where we can't minimize false positives, that's impossible,
Sure.
but, as to 0, but we can definitely get to a point where we're happy with the risk that we're taking. And that was why we chose 0.9.
Okay, thank you.
No worries.
I'm interested in what kind of algorithms you guys were using, because between supervised and unsupervised, unsupervised, recent years we have some breakthroughs on like detecting new unseen malware.
So for this problem where we have labels and everything, so it's very supervised, we tried out all the ones you could think of, so logistic regression, random forests, gradient boosted trees. That's all and well, like you say, like for unseen data, it can handle most cases, but for some of the really new malware, we've moved more into a deep learning paradigm where we can therefore inspect the code. I won't give away the secret, but we have started to use some of that to basically change the way in which you look at the data itself. So we would, instead of just being like, oh, I want to look at signatures or whatever, we're looking at the code itself, the APK itself, or the bundle itself, almost as an image, and then using deep learning on that to find the deeper patterns that we wouldn't necessarily see in metadata or other things.
Okay, thank you.
One more?
Yeah, last one maybe. So for the feature engineering, right, you might have used a lot of things on Spark, on feature engineering.
So yeah, in the feature engineering, got you.
Yeah, so when you're deploying your model and then asking for model execution, right? So was it part of the PMML or were you doing some transformations and then maybe?
Good question. No, we do as much of the feature engineering extraction is done before the model. So the model only really knows about the data from the point at which it's been hashed. So that's where the PMML steps in. So it will go Java, Java up to the point of hashing the fields, and then the PMML would take the hashed output. One more.
Sorry.
This is the most questions I've seen out of any of these. It's great.
Yeah, that's interesting. Most of the samples that you get for your raw data of the APKs, do you have a classified data? Do you know if there are malwares, or you're just exploring tons of stuff?
So we use various ways to label up the data. The primary way is to use third parties, so community-based ratings, and we take like a minimum standard. So we'd be like, okay, if rating agency 1, 2, and 3 agree, and they all have a rating, say, A+, then they're probably it's all fine. But we also take into account our own knowledge. So we have a threat ops team, and they rate the apps themselves as well. So we combine that all together to basically give us a label that we really trust and is seen as ground truth.
Okay, so for the learning phase, it's all done on labeled data?
At the moment, yeah, for now.
Thank you.
Thank you.
Thank you, everyone.